Hey everyone, and welcome to today's Explainer. I'm Dr. Chem, and well, I am absolutely thrilled you're here. Today, we're going to dive right into the seriously fascinating world of physics by building our very own simple electric circuit. Think about it. We literally rely on electricity every single day, right? From the second we flip on the lights in the morning to when we plug in our phones at night. But today, we aren't just going to use electricity. Oh no, we're going to actually control it with our own hands. Okay, so here's our game plan for this lab. First up, the magic of electricity. Then we'll gather our lab materials, build your very first circuit, see exactly how that circuit works, cover open, closed, and short circuits, and finally wrap up with troubleshooting and key takeaways. Let's get to it. All right, kicking things off with part 1, the magic of electricity, from atoms to everyday power. So before we can actually harness electricity, we kind of need to understand the science of what makes it tick at an atomic level. I mean, sure, it effortlessly powers our TVs, our flashlights, our whole homes. But what exactly is it when we zoom in really, really closely? Well, it's like a giant microscopic puzzle. To understand it, we have to look at atoms. They're made of protons, neutrons, and electrons. And let me tell you, when an atom gains or loses those negatively charged electrons, things start to get very, very interesting. At its core, electricity is just this incredibly powerful force created by those charged particles. Now, sometimes it just kind of hangs out as static electricity. But when these electrons start to flow in a nicely ordered path, usually through a metal wire, bam, we get what's called an electric current. And it's exactly that ordered flow that we're going to capture in our lab today. You can actually think of this current as a flowing bridge. That ordered, moving stream of electrons travels right through the cables to deliver power straight into the wall outlets in our homes. It's literally the exact same principle that powers your household lighting systems and all those electronic devices we just can't live without. Moving right along to part 2, gathering our lab materials and preparing the workbench. We're going to conduct a really fun little experiment right now. But first things first, we got to gather up all the necessary supplies for our lab station. For this hands-on demonstration, you're going to need a simple 1.5-volt D-cell battery, a small flashlight bulb, a little bit of tape, and a piece of insulated wire that's about 15 centimeters long. Now, a quick heads up, you'll definitely need a parent or a teacher to carefully strip about 1 centimeter of the plastic insulation off both ends of that wire. We really need to expose the bare metal underneath for this to work. Now, I want you to look really closely at the anatomy of that little flashlight bulb itself. You'll actually see 2 stiff wires sticking up inside, and they're connected by this incredibly thin, fragile wire called a filament. Those 2 stiff wires travel down inside the base of the bulb where, well, you can't really see them. But here's the secret. One connects to the very bottom tip of the base, and the other connects to the side casing. This highly specific design is literally the whole secret to making our circuit work. All right, on to part 3, building your first circuit, a step-by-step guide. So let's get our hands dirty and actually build this circuit together. Just follow these simple steps super carefully. First, grab your tape and securely attach one stripped end of your wire to the flat negative end of your battery. You really want to make sure you have a solid metal-to-metal connection there. Second, place the very bottom tip of the bulb's base directly onto the positive end of the battery, the side with the little bump. And finally, take the loose, stripped end of your wire and just touch it directly to the metal side of the bulb's base. And boom! Just like that, if you hooked everything up right, you've successfully created a complete path for the electricity to flow. It's like magic, but it's science. The electrons zoom out from the negative end of the battery, travel all the way through the wire, touch the side of the bulb base, travel up one of those inner wires, push hard across that tiny filament, head back down the other inner wire to the bottom of the bulb, and finally enter the positive end of the battery. That beautifully continuous loop is exactly what gives us that glowing light. Which brings us to part 4, how the circuit works and the flow of energy. Okay, so now that our bulb is glowing nice and bright on the workbench, let's totally unpack the science behind exactly how this new circuit of ours is functioning. Generally speaking, a basic circuit relies on up to 4 main parts. First, an energy source, like our battery, to provide that crucial electrical push. Second, conductors, like our wires, to hook everything up. Third, a load, like our light bulb, which actually takes that electrical energy and converts it into something else, which in this case is light and heat. And fourth, sometimes you'll have a switch which safely opens and closes the circuit so you can control the flow without having to physically yank the wires apart. Now, the absolute key here is that electricity is picky. It needs a very specific type of material to travel.
Metals like the copper hidden inside our wire, or even everyday aluminum foil, are what we call conductors. Their atomic structure basically lets electrons swarm and flow super easily. On the flip side, we have insulators, things like the plastic coating on our wire, the tape we used, or even glass. They have high resistance. They basically lock their electrons tightly in place, which is super important because it safely keeps the electricity contained exactly where we want it.
Let's move into part 5, open, closed, and short, controlling the current. Look, things don't always light up perfectly on the very first try. That's just science. So we really need to understand the different states our circuit can actually be in. When you have a totally continuous, unbroken loop from the negative terminal all the way to the positive terminal, we call that a closed circuit. But if there's a gap literally anywhere in that loop, like when a switch is flipped open, the current absolutely, positively cannot flow. You can totally see this in action. If you disconnect a wire, the bulb stays completely dark. Why? Because that physical gap totally blocks the ordered flow of electrons from reaching the return end of the power source. It's a fundamental rule. No complete loop means no current, and no current means absolutely no light. Now, here's where we need to talk safety. You have to be extremely careful to avoid what's called a short circuit. See, electricity is kind of lazy. It will always take the path of least resistance. If you accidentally create a path of wire that just loops around the bulb instead of forcing the power to go through it, the electricity just bypasses the load entirely. And without the bulb there to slow things down, a massive, wild amount of current surges through the wire. This will cause the battery and the wires to get dangerously hot. So, rule of thumb, never ever connect the battery terminals directly to each other without a load in the middle. And finally, part 6, troubleshooting and key takeaways, wrapping up the lab. Before we start cleaning up our lab stations, let's review a couple common hiccups and summarize the big key learnings from today's experiment. First off, keep this number in mind, 1.5. Your standard simple D-cell battery provides 1.5 volts of electric potential. Think of voltage as the essential push that gives those loose electrons the kinetic energy they desperately need to travel through our completed loop. Without that powerful push, the electrons would honestly just sit there doing nothing. All right, let's quickly recap the whole shebang. Number 1, electricity absolutely demands a complete, closed loop to flow. If your bulb didn't light up today, I guarantee the most common culprit is just a loose connection. Just press that tape down really hard to make sure the bare metal wire is strongly touching the battery. Number 2, remember that your bulb is actually acting as a tiny resistor. That super thin filament wire makes it incredibly hard for the electricity to squeeze through. The electrons struggle so much that the friction generates immense heat, which causes the filament to brilliantly glow and give us that light. And lastly, safety first always. Never short-circuit your battery by connecting the terminals without that resistive load. To wrap things up, I'm going to leave you with a final, fun little challenge to put your new electrical knowledge to the test. Take a look at these 4 lab setups right here. Which one of these is the true, correctly closed circuit that will successfully turn on the light bulb without causing a dangerous short or leaving the loop open? Look really closely at those paths. Once you figure that out, I challenge you to look around your own house. What other invisible paths of electricity are just waiting for you to close the loop? Keep exploring, stay super curious, and definitely join me next time for more exciting science experiments and lab explainers. Keep experimenting and stay illuminated, everybody.